Good morning, everyone. Welcome to this webinar. So I think we're going to start now. By the time I'm finished with my introduction, this will leave enough time for everybody to come into the webinar. So welcome to the 21st ETP4HPC webinar. I'm Pascal. I'm ETP4HPC's communication manager, and my colleague Mike is also here to help run the show. Hello, Mikey. I will introduce the speakers later. So for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in high-performance computing. And we are a private member of the EuroHPC JU, which is the organization in the European Commission that addresses HPC. And our role is to propose research priorities for Europe in the area of HPC. And that's exactly what we are going to talk about today. So, yeah. So, sorry, I have a problem with my slides. Okay, so before we start, a few practical information. So this webinar is recorded. You will receive the link tomorrow. The webinar is in listen-only mode, but you can ask questions. So if you want to ask questions, please use the question tool. You can also download handouts. We have 2 handouts today for you. First of all, the slides of the webinar, they are available right now for you in the handouts section. And we have also put there the SRA that we are going to talk about today. The PDF is here in the handouts, or you can download it from the ETP4HPC website later on. It's up to you, really. So our topic today is the SRA, our SRA, and we'll do a deep dive on I/O and storage. And we have invited 2 speakers today to cover this. So first of all, Michael, he's our grandmaster of the SRA. So really, he's the one who coordinated all the work, and he's been doing this for quite a while. So he will explain about the SRA, what it is, how they prepared it, and he will touch also about what will happens with the SRA later on. What are our plans? And we have invited Sai. Well, I think he's well known to our ETP4HPC audience because he's he's our vice chair for industry. He's part of the steering board, and he works for Seagate. So thank you, Michael and Sai, for being here today. We're looking forward to your presentation. So this is the agenda, very straightforward. First, an introduction by Michael. Long introduction to explain about the SRA, and then Sai. And we will take all of your questions after the presentation. So you can send your questions whenever you want, but we will take them at the end of the presentations. So Michael, I will give the floor to you. So now you should be able to share your slides.
Yeah, just 1 second. Do you see the slides?
Yes, we do.
Okay, good. So thank you very much, Pascal. I'm pleased to give you a little insight into the SRA 5, and I decided to also have a few charts on the next steps so that you all already can understand where are we going next and what is on our plate. So, okay, so SRA 5. This is the 5th time that we do this in 10 years. So almost every 2nd year we issue such a document. I mean, each time we do this, it becomes thicker and more comprehensive. So it's 160 pages now, 10 working groups, 25 work group leaders. There are a few of them also on the call. So besides Sai, I saw Robert, Maria on the call, so welcome. And we had roughly 120 work group contributors. So I think quite a number of participants. So you can basically say, okay, the SRA is not something that a few people just wrote up with the potential impact that this is not reflecting, let's say, a broader consensus of the ecosystem players. This is really reflecting what experts in this area think and suggest as R&D challenges for the next years. Okay, so let me give you a little navigation help. I did this already some time ago, so some of you might have seen this. If you haven't looked into the document, this might be helpful. Otherwise, you know what I'm talking about. So in chapter 1, we basically start with outlining. So why do we do this? How is this document coming along? The process of writing the SRA, the working groups, how do we structure the content of this deliverable? What are some of the global challenges that the HPC space encounters? The need for worldwide collaboration is a hot topic here. We briefly introduced Euro HPC, of course, only with a few sentences, because there is a web page you know about Euro HPC to begin with, and then right in the beginning we talk about European digital sovereignty, which is also very important to the ETP and to us. So then in chapter number 2, we basically would like to show that the previous SRA 4 had good, let's say, influences on real projects. So there are quite a few projects that relate very nicely to contents being displayed and being written up in SRA 4. So there's a connection here, which proves that the SRA 4 at least was instrumental in getting things going for these projects. And we hope, of course, for the same to take place again with SRA 5. Then, I mean, each time we issue such a document, we think about, so what is the overarching, the big thing that we'd like to propose? This time, we'd like to propose sustainability, because I don't need to explain this, because it's on the TV every day that we are suffering from environmental impacts, and HPC has two facets in this. Has a positive facet because it helps understand the phenomena. On the other side, it has a negative impact because it uses resources and it has a certain CO2 footprint. And understanding both sides and reducing the negative impact is what we think would be a good new topic, an overarching topic. The one from SRA 4, which is this digital continuum, and we call this TransContinuum, that has grown up very nicely, and this is why I wanted to have a few new insights into that spectrum, after having done this SRA 5 introduction. And we continue on this path, as you will see. Then there is a section on industrial use of HPC, which has been put together with the help of the project, one of the projects, HPC Gig. And we go to the next page. Page 5, you know about the 3 prototypes being put in place: UPEX, EU Pilot, and HPC QS. They're being briefly mentioned here, and this will be interesting for the next 2 or 3 years. We are going to follow up, certainly in the next big conference in March in Gothenburg. They will be also discussed, they will be presented, there will be a session on them at the Euro HPC Summit Week. So we briefly introduce them here, and you can follow up with more detail then during that session. And then comes the core of the document, the technical research priorities. As in SRA 4, we said we cluster them into two views, orthogonal views: research clusters and research domains. I'm going to talk about this a little later. And this content here is totally new, although it looks like the headings are almost the same as last time. The content is not the same, of course. Open source approach. We put more emphasis on this than last time because we know that there is a strong movement towards open source software and hardware for future systems in Europe. So this is a hot topic. And as it is hot, we know this, we wanted to give a balanced view about the pros and cons and about the let's say, sensitive aspects that need to be taken into account when you engage on an open source project. The biggest concerns are, or let's say the biggest issues here might be if you do a major open source hardware project. Building on retaining skills, it's always, let's say, a topic since SRA 1. Then operational recommendations. How should Euro HPC run projects? Should there be not a holistic project management approach? We say yes, and we explain this again. And then conclusions and the appendix. So you can pick and choose where you start. I wanted to display this here. So here you see the groups and the participants. And in the call today, we have Sai here as one of the working group leaders from IO and Storage. I saw before also that Maria Perez was involved here. She's listening, and she was one of the leaders of the system software management team. And then we have one of the new working groups called Non-Conventional HPC Architects, and Robert Haas from IBM Research is one of the two leaders there. So the point here is that you can see that many people have been participating. And the point of this chart is that writing such a huge document certainly has disadvantages because it's hard to keep the focus for 2 years on getting this done. The positive momentum I felt also based on feedback from the work group leaders is that this is a community action. It's basically pulling people together, make them talk to each other, share ideas, and feel like we are in this thing together. So that was appreciated very much, and I think if we will be talking about next SRAs, or maybe we're going to do them in a little different fashion as white papers, this aspect has to be taken into account, the group building aspect of writing such a document. All right, now the research clusters and research domains as last time. This orthogonal structure, we have new clusters. One, which we want to make the overriding cluster, is sustainability. Then, of course, we touch on digital continuum, HPC for urgent decision-making, federation of HPC resources, and heterogeneity of architectures. These topics here change from SRA 4. They basically reflect what is hot now, what is hot for the next few years. And then on the other side, the other domain, we basically say, okay, these are the layers of the HPC stack. We have two new aspects because we thought we need to talk about hardware also from a new angle, being unconventional architecture levels. And we need to, of course, introduce also quantum for HPC. So those two are new. By the way, you might have seen white papers associated with these two new working groups. And when you put this together, then you basically can distill out of the text the crossover points. So where, for instance, what is important in the area of system architecture for the in terms of heterogeneity or for sustainability? This is the way you should be using this information. Very important is the role of the SRA in the context of future influences on work programs. And this is different from SRA 1, 2, and 3. In those days, we were in a CPPP with the European Commission. We issued the SRAs, we talked to them directly, we tuned a few words, and then, our proposals, for the most part, made it into the work programs. This is now much more indirect because we have the RIAC and we have Euro HPC, and those two levels have their own ideas about work programs. So they are using, hopefully, to a larger, more or less large extent, what we write up. So this indirection is something that is, let's say, a little harder, makes our lives harder. And we discussed this with other organizations, like, for instance, the 6G SNSJU and the KDTJU. So wherever there is a JU in the middle now, right? And also for the IT space, this phenomenon is always the same, that these private associations feel like all of a sudden their input is really has to be taken onto a much more indirect path, because the organizations, the GUs, have their own saying, and the political influence is bigger than before. So that is a sensible or sensitive area. Otherwise, I mean, ideally our SRA, and there is a chapter with showing some of the project being initiated based on SRA 4. So it works to some extent, but how effective is this arrow here? That will also be discussed to some extent on our GA meeting in March. So stay tuned if you have input here, if you have ideas for getting this circular thing continue to work perfectly, then speak up. All right, so now comes my little, and I think I need to speed this up a little bit. The TransContinuum initiative.
Yes, please.
Yeah, so how many minutes do I still have?
7.
7, okay. So you know about the TransContinuum initiative. Let me run through the new stuff here. So we started this continuum about 2 years ago. We had some use case reviews. We now think we need to come up with a third step. The second step being our involvement as a consultancy support to Destination Earth. You have heard about this before. We think that the third step, so use cases first, Destination Earth second, now a third step should be TransContinuum by design. What do we mean by this? When you look to big infrastructures, and there are many, right? So for instance, autonomous driving, the federation of resources over your HPC supercomputers, the telco infrastructures, you have many of those. Then you realize that they have been put in place to some extent by focusing on specific aspects. And there are phenomena today that suggest that there needs to be an end-to-end design effort in many of these areas, focusing on interoperability, reliability, availability, serviceability, efficiency, which is sustainability and cybersecurity. So you might think, well, this comes by nature, and this has been taken into account. That is not necessarily the case. 2 small examples from an area which is maybe not on your radar screen every day. I mean, you see that the energy crisis is limiting now the use of big instruments. So the LOFAR system in the Netherlands has been limited in its operation by energy. And there was a cyber attack on the Atacama Large Instrument Observatory in Chile. So these things happen. Maybe we do not notice them, and they might happen more in the future. So there is the statement that many things need to be redesigned or maybe taken into account looking at the end-to-end phenomena. So when you think about what needs to be addressed as a continuum, then be aware of if you optimize one element, you might have an impact on the other one. So if you optimize the energy efficiency of an HPC center, you might compromise networking speed and data throughput. And this is why this is so complex. And here, the red sentence, if you're summing up and interconnecting locally optimized elements, the entire solution might not be running optimal. And so a global optimization is not the same, is more actually than connecting the sum of local optimizations. And when you want to put this onto on a bigger level, then you could say, well, what we are driving for here is a sovereign sustainability. Sustainability in these three dimensions: societal, environmental, economic. And sustainability, we talked about serviceability, power efficiency, reliability before. You can move all these detailed aspects under the umbrella term of sustainability. And sovereign means we need to be able to produce these infrastructures, keep them operating with European efforts, mostly reducing the dependency on other supply chains. So what we are saying is now this continuum is the associations behind this. They want to become instrumental and more helpful when it comes to design work programs. With this end-to-end continuum design as a main thread and idea. And we would like, when it comes to large-scale instruments or large-scale pilots, actually, I think we can deliver, and HPC is part of this, so the ETP is part of this expertise and assessment. So that is our next step. So this means we need to get engaged with the European Commission and somehow rally up between all these associations to influence work programs. And with in respect to large-scale pilots, saying, okay, we could play a bigger role here. And one example is, of course, our support for Destination Earth.
Okay. 2 minutes left, Michael.
That's perfect. Yeah. So I talked about the open source approach, a balanced view. If you would like to have more information besides reading through the SRA, there is a white paper issued some time ago, which basically also issues recommendations for software and the hardware part. This is the operational recommendation. So we think that ideally, how do you organize R&D in a big company? You have a multi-layer aspect, making sure that innovations comes into your organization, but not every, let's say, idea, of course, is going to be fruitful for future products. So you have stages here, you check them out, you only support with more money things that are more promising. So this kind of a scheme, I think, or many think, should be adopted also by EuroHPC, because EuroHPC is working with this view of, okay, we want to have a sovereign HPC infrastructure in Europe. So instead of funding many things in parallel and which are not really correlated, it would be better to look at this from a more holistic view. That is our point. Sustainability, and this is my last chart. If you are interested in supporting us, we have a working group. It hasn't really done much, but this is on our stack now. If we would like to focus on describing the software aspects of improving sustainability. So system software and application software layers, what can they do in order to make the operation of HPC centers and the execution of workloads more efficient? If you're interested to contribute here from a software perspective, we leave the hardware part to other organizations like the KDTJU. But if you're interested in the software part, you're welcome. Send me an email, and we're going to have a kickoff meeting very soon. So I guess, Pascal, that was it, just in time.
Thank you, just on time. Excellent. So I will hand over to you to share the slides.
Yeah.
Now you should be able to share your slides. So just a reminder to all of our audience, you can ask your questions in the question panel. Feel free to do it at any point, but we will answer your questions at the end. So Sai, yeah, we can see your slides, so
yeah,
please
great.
go ahead.
Thank you, Pascal. So today I'm just going to present a summary of what our SRA team have concluded from our work on looking at the state of the art and future directions on storage and IO perspective. And this is also not, I would also like to very much thank my co-lead, Professor Andre, Dr. Andre Brinkman, and also the entire storage and IO team. I mean, who have really been instrumental in getting all this material together. So it wouldn't have happened without everyone's efforts. So I'm here presenting a summary of what we have concluded at the time of writing this SRA. And it's been a very interesting journey for me because I've been involved since SRA 1, leading the storage and IO work group. So it's interesting to see the journey over the last 10 years, how storage and IO has evolved in the HPC landscape. Let's go to the next slide. Yeah. So just some of the top level trends that we see in storage and IO at the time of writing this SRA, SRA 5 is we continue to see very large, very big convergence between HPC, AI, and big data. So when we started off a few years, when we started off writing the SRAs, it was all about HPC IO simulations, middleware, MPI IO, and these kind of things. And then towards 2013, we started seeing big data analytics coming into the picture, like all the Hadoop and HDFS and these kind of things. And now it's all coming together. Now we have AI. So HPC, AI, and big data, they're all part of the same big scientific workflows. And you should be able to design the storage that can accommodate all these different types of personalities. So that's why we call this the age of convergence. And what's eventually happened is that there's increased bandwidth requirements per node in the HPC, and the access patterns have become more and more complex. So when you used to design storage just for sequential IO, just for HPC simulations, it just used to be for things like checkpointing. You just had to deal with sequential HPC workloads, but now it's completely random workloads as well. It's random workloads, read and write, and mixed read and write. It's all the demands on the storage are intense because all these applications are very scientifically very IO intensive. So this has posed a lot of challenge for the storage system. Then the other top level trend is the age of accelerators and coprocessors. We used to have our GPUs come into the picture sometime early on this decade, but now we have FPGAs, and now we have the TPUs and DPUs, which all form part of your data pipeline. So there's also the core counts continue to increase. So what all this has caused is that the performance gap between the storage and the compute just keeps on increasing and increasing and increasing. The bandwidth to storage has also increased, and the capacity of storage has also increased, but it's never kept pace with the pace at which the compute nodes have increased their capacity. So that's actually an interesting challenge for the storage and IO community, technology community. And there's coupling of data from multiple sources. Needless to say, there's data coming from IoT, there's coming smart cities and satellites and every sector that you can think of, like agrarian or finance or health. There's just data coming from multiple sources, and they need to be part of the scientific workflows. And there's also a need to distribute this data processing to the edge locations as well, which is the other challenge. So that is one of the other trends. And then we have new interconnect protocols like CXL. Gen Z is of course been imbibed into CXL now, and there's non-volatile memories which we have seen since 2015-16 timeframe. So it's already been accommodated in some very large systems now, and even the software stacks have been designed to accommodate non-volatile memory. But there are some challenges associated with that as well. I'll go into that in a second. Let's go to the next slide. So just a retrospective. So these are the technologies that have become mature since we assessed them in SRA 3. One is object storage in HPC, and then non-volatile memories. We kept talking about this since 2016, 2017. That there are issues with this so-called POSIX APIs. There is no real need for strict consistency, and that there's a need for very flexible data models, etc. So some of the projects, storage and IO projects in Europe, like Sage and Sage 2, so they started looking into some of these object stores, and even globally, we see that some of these object stores they've gained a lot more traction. And for example, DEOS has been will be used as primary storage in Aurora exascale machine. So we see object storage more and more in HPC. And non-volatile memories, we saw that in the NextGen IO project as well as the Sage and the Sage 2 projects experimentally. And since the time that we have started playing around with this in the projects, they have been commercially available, and they're available in different form factors. So yeah, and the new projects, IOC and Admire, they continue to work on these topics as well. The HPC data centers in the cloud, they are coming together. So just to give some examples of large initiatives that have been built around them, there is the Gaia-X initiative, for example, which is trying to get together all the infrastructure ecosystem under one roof and also have a data ecosystem on top. So HPC is clearly, for example, shown as one of the pieces of this infrastructure. And Gaia-X is just one example. Even there is also new frameworks like the simple middleware that's being proposed by the EC. So they're all looking at this federation of data sources, and HPC data centers and the cloud, they all form a part of this federation. So because there needs to be data sharing and data ingestion that will be part of the scientific workflows. It's not just for the cloud workflows, but the scientific workflows have this aspect of data sharing. And what happens is that there are new problems with such close overlap. There is needs for identity and access management, resource management, trust, security, infrastructure monitoring. So those problems will be there to stay. Then, so APIs, the cloud APIs like S3, popularized by Amazon, they have been used in, it's a nomenclature that we use in the cloud world. But now it's not the case, not just the case. Now, even in the realm of HPC, the research that we have been doing, we have been actively using cloud APIs. So we already see that in some of our research activities as well. So then the distributed data processing aspect, where this data processing units, data processing that needs to be done across multiple data centers, and they all need to be brought together. So that aspect is very clearly there. And we see some examples of this federation of data and compute management across HPC boundaries in initiatives such as Phoenix Research Infrastructure. I would encourage the audience to go and have a look at that. And the one thing to note that bandwidth and latency are not solved problems at all. So when you have this federation, when you have these data centers, when you have these HPC sites that are distributed geographically, the data sharing becomes a very, very big problem, especially when the data sets are very large. And even today, the best bandwidth that you can get is only through a truck that is loaded with hard drives going from A to B. So there is no other better way to solve this problem. So that's still, and data is just going to only increase over time. And you can have, of course, intelligent caching, and you can move compute to data. You need to build on all those kind of things, but fundamental problem of bandwidth and latency still is there. So also with these kind of federations, you'll have the issues of metadata management and making data locatable and manageable. Those continue to be even more harder problems. So then there is this new processing paradigms, as I was mentioning, all these new animals in the zoo or new kids on the block. So DPUs, which are now quite spoken of. So DPUs are tightly coupled with network interfaces, and we see a lot of opportunities from the area of storage and I/O here. So for example, if you look at file systems that are used for HPC, they have huge processing requirements. Like for example, if it's using the Ethernet or if it's using the TCP/IP stack, there's so much processing involved there, and there's the aspects of encryption, and there's the aspects of error checking. They're all quite processing intensive. So all these things can be smartly offloaded to some of these new hardware paradigms. And GPUs and FPGAs can be very, very interesting for on-the-fly data processing as well from a storage and I/O perspective. And we need to look at new processor designs as well, because the new instruction sets, the new instruction capabilities of ARM, and also RISC-V, there might be opportunities for the storage stack to exploit some of these features. So this is continuing work in progress. And non-volatile memory, it's used in the storage hierarchy, and it can be used as a block or as an extension of main memory. And you can deal with that in 64-byte cache lines, where you can directly load and store without going to the main memory, which is very handy. And it can be a metadata store for file systems and object storage, providing very fast access. And you can also use it for local checkpointing of your data in a very fast way. And also it can be another tier in your latency performance curve. Like there can be a SSD tier, a HDD tier, and NVM provides another tier for that. So it has been used within our projects. In the next gen IO project, we have used non-volatile memory, the Optane memory from Intel, and it's also been used in the Sage and Sage 2 projects as one of the tiers of storage. So having said that, I would like to also point out that there's a gap at the moment, because 3D crosspoint is discontinued. So that was the main technology out there for research to assess non-volatile memory, but that has been discontinued by the vendor. So this is an area, I think non-volatile memory is very relevant for the HPC IO stack because of all the flexibilities that you get, but we definitely are looking for some kind of support from the ecosystem and from the technology providers in terms of like new technologies that can be assessed in this light. So, and POSIX and object storage. So there are consistency and correctness issues with POSIX, and it poses severe performance constraints. So object storage provides this relaxed semantic. So as exemplified by some of the research in Europe as well as globally. And the good thing about object storage in HPC is that it can provide this nice plug and play capability. So you can have your object storage be your foundational layer at the bottom dealing with the data. But on top of that, you could have the objects, the applications look at objects as files or as HDF5 units or as PNFS parallel file systems or as POSIX. So you can build all these kind of adapters on top of object storage. And with object storage, there are also better opportunities to include new capabilities like telemetry, quality of service, and also in storage computing. So then if you look at AI and deep learning, so if you look at that community, there are so many tools out there. So they all need to somehow smartly work with our community, with the HPC IO stack. So for example, one of the previous research projects, Sage2, we looked at a TensorFlow plugin for object storage, for example. The challenge is that most of these infrastructures work with POSIX style APIs. But when you are starting to deal with object storage, then there needs to be proper APIs to actually work with object storage in the context of HPC. Tape. So every time we hear this, is tape dead? But we would like to say tape is immortal for now, because tape is still the cheapest storage tier, and it can host very, very large experimental data sets. They provide very low latency, though access in a timely manner is an issue. And there are still issues with indexing and data labeling, identification, etc. But tape is definitely part of this HPC IO stack way at the bottom. And it needs to be that way, because that's how we can get access to very old data if that needs to be part of your scientific problem. So you need to bring that into the fold. And there are already initiatives out there in Europe, such as some of the, for example, the Phobos initiative from CEA, and also it's also used in some of the projects such as IOC to access. There's methods to access tape in a software specific access, viewing tape data as objects. So that could be that would still be very interesting. And there are some also interesting techniques to work with cold data as well within the European ecosystem. For example, the data carousel scheme at CERN, where there's a sliding window across the tape and you load some part of that data onto the disk. So that's also quite interesting. And I have a couple of minutes. I'll quickly speed it up. So understandability and machine introspection. So something to note is that when you build these complex hierarchical storage and all this complex IO stack, storage is just going to be a norm rather than an exception. So you need deeper understanding of the storage infrastructure. You can't go through unstructured logs. So there's a need for AI tools to actually work on the telemetry data that comes from the storage and IO stack. So that is still an open problem, and there is some early work done in the context of European projects. As my colleague Michael was pointing out, sustainability is extremely relevant for HPC. I'm just reinforcing that message here, but also from a storage and IO perspective. So in energy efficiency is driving optimizations across the hardware spectrum. All the vendors are doing that. The technology providers are very keenly aware of that. But the data movement considerations are given lesser attention. How do you optimize these data movements? How do you move compute to storage? How do you move compute to the edge? So these kind of smart movements of the smart scheduling that needs to be taken into consideration, and keeping also cold data in the tiers that consume very low power has to be done, and also ways to increase the longevity of existing storage technology by using smarter hierarchical storage. That all forms part of that green solution. And also things like recycling and reuse of HPC storage hardware has to be borne in mind. So last couple of slides here. So just some examples of cutting edge research going on in Europe at the moment is one in the storage of IO and storage. So one of them is the IOC project, So it's part of the C projects, which deals with this modular supercomputing architecture, which has elements of compute and network and storage, exemplified by the Deep C, Red C, and the IOC project. So IOC looks at storage. So it's about working with these on-demand services, so-called ephemeral services like NFS, S3, POSIX. They're spawned on demand, and they work with object storage on the back end as needed by the applications. And the data moves across these tiers managed by object storage and the tape by policy engines and hierarchical storage management methods. And there is smart ways of monitoring, instrumenting all this IO, and also doing some AI-based analytics on that. So I would encourage you to please have a look at the C projects website, and also the IOC project. And then this is the other very interesting project focusing on IO and storage. It's the looks at adaptive multi-tier data management. The idea is to develop this very active IO stack and dynamically adjust your computation and storage based on the need through some very smart coordination. And you schedule storage resources across these multiple hierarchies. And there's some very interesting applications that the Admire project is looking at from all these from all these different areas. So yeah, I would like to conclude my talk here, and thank you, Pascal, and everyone for giving the opportunity.
Yes, sorry, I'm taking back control. So yes, so question time. So I have started receiving questions. So if you have questions, do use the question tool, and so everybody can see the questions. I'm copying them into the chat. So if you look at the chat, you will see all the questions asked by the audience. So we have 2 questions. Let's take them in order. We have a question from Maike here. Actually, she could have say this. What do you see for assuring the AI HPC convergence on data side?
So yeah, thanks, Mike, for that. I think the first thing is that we need to do. We have continued to do this co-design in our HPC projects. We have co-designed with classical simulation applications now. Then in some of the projects in Europe, we have looked at classical HPC and big data intensive applications together. I think we started to do this co-design with the AI applications as well. We need to look at these workflows that have very strong AI component and do continuous co-design. So I think that needs to be done, because we are still learning about these AI applications, like for example, random accesses and things like that. And how do you design your caches and your burst buffers? How do you like size them? So all these kind of things we continue to learn. So I would say that that should be part of your co-design cycle for storage and IO.
Okay, thank you, Sai. So there is a question from Fabrizio Maguliani. Is quantum computing posing any specific requirement with respect to storage?
Yeah, that's yeah, very interesting question, Fabrizio. To be honest, we are learning. So this question does it's not the first time I'm hearing this, but I don't have an answer. So we are still learning about this, and I think maybe it's an opportunity for some of our upcoming research projects to actually specifically look at the data aspect of this and drill into this a little more.
Okay, so lots of work for our SRA experts then. Another question from Fabrizio. Thank you, Fabrizio. What storage and IO technologies are most promising for a reduction of power consumption?
Yeah. So I think essentially what I said is, I mean, hierarchical storage is very interesting because you can actually place your data anywhere in the hierarchy, and you can have policies for data movement based on cost, based on performance, and based on power. So you can actually smartly move. Power can be one of your optimization criteria. And for that, in terms of storage technologies, as I was mentioning, so tape is still is still very low power, and it can still be used. But however, even from there are technologies within, for example, RAID, even within the even when you build enclosures and things like that, there is things like there's like technologies such as massive array of idle drives, where you make sure some of the drives are idle all the time, and you can smartly turn off some of these disk drive functions when you don't need them. So you can actually do some of these smarts for actually reducing your power consumption. But I would still say that the smarts needs to be in the software, how you actually deal with optimizing your power across your entire HPC IO stack, because storage is not just the storage technology, but the IO stack starts from the compute. Working with the compute clients are sitting there working with the cores, and then you start working on even the network needs to be part of the picture, so you need to deal with all of that.
Thank you, Sai. So you get all the questions, Sai, because I have another one for you from Rui Machado. Sorry if I mispronounce your name. From Fraunhofer. What are the most important challenges when considering data movement and related to that tiering?
Most important challenges for data movement related to the tiering, I think what I would say is identifying when you need to move the data to what tier at what time. So that all depends not just on the data administrator, but that also depends on the applications as well. And as we showed some of these projects, so some of these applications, they spawn some of these services on demand. Like for example, there might be a NFS module that's spawned on demand, or an S3 module spawned on demand, or the applications have just ingested, the scientific workflows have just ingested some data sets from somewhere. So all that will actually drive when you need to move the data to which tier. And the biggest challenge is to just bring about this coordination. So there needs to be coordination with the schedulers and with the workflow managers and with also the hierarchical storage management system. So the challenge is putting all these software pieces together, I would think.
Thank you, Sai. More for you, I'm afraid. Actually, we have Robert Haas is saying hello. He's online. He's one of the big contributors to the SRA. So, hi, Sai. I obviously like to see tape being highlighted here, but what are your thoughts in exploiting AI to predict data accesses beyond the typical temperature-based tiering approaches known today?
Yeah, I think that's definitely a very good and relevant question. We need to use data. We need to use AI tools more and more to predict, do prediction of data accesses. From even I think from a workflows perspective, it's if we are able to, based on past prediction of these IO of these scientific workflows as to when they actually do the IO based, if we are able to come up with some techniques and methods as to next time when they are scheduled, how's the IO patterns going to be, and when are these IO windows scheduled, and what are the tiers that are going to be used. So if we actually use some AI methods to predict, to actually learn from these workflows as and when they're, or these applications as and when they are scheduled, so you can actually already do some very efficient and intelligent data bringing data to the right location at the right time. So yeah, that's one way, is to actually work at the top level. Apart from, of course, the temperature-based steering. So that's just one thought. I'm sure you know, my SRA colleagues will have a lot of other more interesting ideas as well. It's something that just comes to mind. Yeah.
Okay, well, thank you, Sai. That's all for the moment. I don't see any questions, but we still have a few minutes. So if you have more questions, do enter them in the question tool. And while we are waiting for more questions, I just wanted to announce our next webinar. It's in 2 weeks' time. It will be another webinar about the SRA 5. But we will focus on a different topic. We will focus on federating HPC, cloud, and data infrastructures. So if this is an area of interest for you, please join us on the 16th of December. And yeah, and we have a new question. So this is a question from Fabrizio. I'm glad we have you, Fabrizio. Will AI use more energy than it will be saved on the I/O storage?
Interesting, Fabrizio. I don't know the answer, to be honest. So we can go into a discussion here. Yeah, I mean, if you want to do all this smart tiering, smart telemetry and analytics, if you want to do all this smart placement, then obviously you are going to assign resources to all those smarts, and we need to look at the system holistically in terms of different optimization criteria. If it's like time, if it's like time to completion, if it's like time to solution, or is it energy to solution? So if you have to optimize for those kind of parameters, so then you have to adjust your the different tools and the different daemons that you run on the system, the AI daemons and things like that. So it might be a very smart I mean, opportunity for research projects to look at this holistic optimization of storage and IO. Considering that we need to work with these new AI tools, and we need to understand the energy impact of those things. At least we guys from the HPC and HPC storage and IO side. Yeah.
Okay, thank you. Fabrizio is sending a smiley. Next time, Fabrizio, we'll have you on the Q&A panel. Okay. I don't see any more questions coming. Michael, did you want to add anything before we close the session?
Well, we can only make some more PR for our sessions. So we might think about continuing this sequence with other areas from the SRA 5 in the next year, in January, February.
Yeah, that's a very good point. Actually, if some people in the audience have an interest in a specific area and would like to have a webinar about it, please email us. You can email webinar@ETP4HPC, and I'm getting the email, so I will transmit it.
And of course,
thank you, Michael.
to have sessions then also at this EuroHPC Summit Week, Pascal, right? So
yes, we will be at the EuroHPC Summit. So yeah.
So also refer
some of the topics, not everything, but
no. Yeah.
Okay. Well, it's almost time. So, Sai, anything you wanted to add? No.
No, thank you, Pascal.
No.
And
okay.
Yeah, thanks for the questions.
Okay, well, thank you. Yes, thank you for the questions. It's always great to exchange with the audience and to see your interest in the topics we propose for our webinars. So I will just thank the speakers. Thank you, Michael. Thank you, Sai, for being here today. And I hope we'll talk to you, all of you, in 2 weeks' time for our next webinar. Thank you very much. And thank you, Mike, for supporting me. Bye-bye.
Bye.
Okay, bye-bye.